Let's get started with looking at writing a MATLAB code for encoding the LDPC codes in the 5G standard. So on the left side here you can see my folder. It has the .m files that we have created in the past in this course, and a few PowerPoint presentations and some .mat files. So there's also a folder called base matrices. Okay, so if I blow up this folder, it has all the base matrices which are there in the 5G code. Okay, so it has all the base matrices as text files, and I'll show you maybe one text file opened here. Okay, so this is again a MATLAB editor window in which I've opened one of the text files. In fact, two of them. This says NR1 to 20. So this is just my notation. The 1 means it's the first base graph. 2 is I think j equals 2, and then 20 is the expansion factor. Okay, so this is a base matrix. The first base matrix, if you remember, the first base matrix is 46 rows and 68 columns. Okay, so it goes all the way up to 68, and if you go up and see in the first 4 rows, right, the first 4 rows, you will have the double diagonal structure. Okay, so the double diagonal structure sort of starts here. Okay, so you can see that right there, right. So the double diagonal structure starts there, and this part is the double diagonal. Okay, so likewise you will have in every single code, and in fact this folder will be made available to you. You can download this folder with all the base matrices, and in your working directory, in whichever computer you are using, I would suggest that you keep this so that you can access the base matrices whenever we want. Okay, the base matrices will play a very important role, and that's something you have to do. Okay, so let me show you how one can load, etc. So I am in this directory, the main directory, and let's say I want to load the one of these base matrices, the 1, 2, 20 that I showed you. So I could do this. I can do load base matrices / nr 1, 2. You can even do a tab here. You'll get this thing. So it will load that matrix into your workspace, and the file that it will give is nr_1_2_20. That's a bit unwieldy to deal with, so I usually like to do this. So this brings that matrix in for me. Size of B is 46 by 68. Okay, so 46 by 68, that's 22 block messages. Each message block is 20 bits long. I told you this NR1 to 20 gives you an expansion factor of 20. So 22 into 20, that's 440 bits of messages. Okay, and how many bits of code words will come out? 68 into 20. 1360 bits of code word, and 22 into 20, 440. Okay, so the slight caveat here, I have to warn you, 440 message bits is okay. That's the message bits that will come in, but usually when you transmit your code word in the LDPC standard, the 5G standard, the first 2 message blocks are not transmitted, they are punctured. Okay, so the maximum number of bits you will get is actually 66 into 20. That's 1320. Okay, so the lowest rate you can get is 1/3. So in fact, people also don't transmit all the parity bits. They'll transmit as many parity bits as they need. Okay, so you don't transmit all the parity bits, so you can get different rates that way. Okay, but for now we won't bother with those kind of things. We will just work with the entire matrix and see what we can do. The puncturing of the first 2 blocks alone we may consider, but generally this is the picture. Okay, hopefully this is clear to you. Okay, so I'm going to write a little piece of MATLAB code for generating these bits at random, and then doing the encoding, both the double diagonal part as well as the main diagonal part, which is slightly easier. Okay, so hopefully this is clear to you. You will see it's a relatively easy program to write. There is one little component one needs to take care of, but other than that, it's a easy enough program that one can write. So let's get started. Okay. This is the editor window, so both the files are here, so I'll take out a new one. Okay, so the first function I'll write is a little bit of a utility function. This does multiplication, so I'll say y equals, so I'll call it multiplication shift. Okay, of a vector x by k. Okay. So, this is basically if you remember, every block of the message gets multiplied by a shifted identity matrix. Okay. So, this does that. Okay. So, multiplication by the shifted identity matrix. Okay. X is my input block, okay, and k is the shift. Okay. So, that is the way to think of it. Maybe I should write that down. X is the input block, k is -1 or shift, okay, y is output. Okay. So, there is a little check you have to do here. If k is -1, then y equals y is just 0, zeros of 1 comma length of x, right. So, as many bits as there, else y is x of, remember MATLAB has indices starting from 1, okay, while k starts from 0. Okay. So, if k were to be 0, I have to put out the whole thing, right. So, k plus 1 to end. Okay. If k is 1, I have to start from 2, okay, and then you go from 1 to k. Is that okay? So, think about what this is doing. This is doing the multiplication by shifted identity. Okay. So, let me save this mul shift. So, this is my little utility function. Let me show you a little bit of an example. So, it is good to see how this function works. So, let us take 0 1 0 1 0 1 0 1, okay, length 6 vector, and then maybe we do -1. Okay. So, this is supposed to multiply by -1, I will get the all 0, I am getting that. So, let us say we do 0, I have to get the same thing again. Okay. Once again, remember what needs to happen. If you want, we can write a little bit of thing here. So, what is this mul shift supposed to do? Okay. So, if I have a matrix like this 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1 1 0 0 0 0 and then 0 1 0 0 0. If you multiply by a vector x1, x2, x3, x4, x5, what are you supposed to get out? You will get x3, x4, x5, x1, x2. Okay. So, if this corresponds to k equals 2, okay, so it needs to start at 3, right, k plus 1 till the end, okay, k plus 1 till the end, and then 1 to k. Okay. So, this is what I did here. So, that needs to happen here. So, you can see that is happening. So, when you put 1, it got shifted up and the 0 went to the last. Okay. So, if you put 2, the same thing happens. Okay. So, this is doing the multiplication correctly. So, let us do up to 4 then. So, the mul shift is working decently. It should work even for larger ones. It is a small piece of code. Okay. So, once I have this, another useful piece of code to write is checking whether a code word is valid or not. Okay. So, what should checking whether a code word is valid or not? You are given a base matrix and you are given the expansion factor and you are given the code word. You have to multiply the expanded base matrix with the code word and see if you get all zeros. Okay. So, that is checking validity for the code word. So, let us call that a new function. So, the answer is actually yes or no. So, I will just call it out, okay, equals check code word of base matrix. Okay. The size is not so important, but the expansion factor is important. I will call it Z, and then the code word itself. Okay. So, I will call it C. Okay. So, let us say C. Okay. So, B is base matrix, Z is expansion factor, and C is code word. Okay. So, that's what it is. Maybe we should just save this. Okay. and it will tell you 0 or 1. Out will tell you whether you are right or wrong. Out is equal to 1 if code word is valid, 0 otherwise, 0 else. Okay. So this is what we need to do. So we need to write a little piece of code to do this multiplication. So I'm going to keep it very simple. So I'm not in this lecture at least going to try and write very efficient MATLAB code. I'll just write the simplest possible MATLAB code that one can get. Okay. So I'll call m comma n as size of B. This tells you the number of rows and number of columns in B, and then for every row I have to do something. Okay, for every row, this is the ith row. In the ith row, what do I do? I have to do my multiply shift, right? So I'll keep the okay. So it's good to do it in multiple ways. So one of the things to do is the out we can initially assign zeros of m into z of 1 comma so m into z comma 1. Okay, so this is the output after the thing has been multiplied. I'm sorry, this is not the output, this is the h times. So this is syndrome. Okay, so syndrome is h times the code word, okay, or the received word, okay, to see if it's valid or not. If syndrome is all 0, then it is the valid code word is valid. So this is h times C transpose. Okay. So what do I do here? So it's all initially 0. So I'm going to go through every column, 1 colon n. So I'll say sin of so this the first block is controlled by I, right? So one can think of this as I times, so I think it's I minus 1 times z plus 1 colon I times z, right? So this is the block of the syndrome, and this equals just the same thing, plus the mul shift of C of, right, j minus 1 times z plus 1 colon j times z. Okay. So once again, I'm not trying to be very efficient here, b of I comma j. Okay, so there's also a modulo operation here, comma 2. Okay, so this is reasonably all right. It's a bit inefficient, I will agree with you. If you look at it, those of you who know MATLAB coding very well, you will identify a lot of things here which I could have done differently. There's also this confusion between the row and the column. I'm thinking of the code word as a row vector, and I think this command should work. It should adjust the row and the column suitably. In case it complains, we'll see if there's a problem or not. And then I'm using the mul shift to get the multiplication done, and I'm technically adding a row to a column, but I think it should be okay. This should work out quite okay, I think. So let's see if there's a problem. We'll make an adjustment. We'll have to just put a transpose in one of those places. Okay. So this is done. So this tells you what it is. So if any of sin, okay, so if any of the things are non-zero in the syndrome, you can set out equals 0, else out equals 1. Okay. So that's the final thing. So this is just computing, checking whether a particular code word, a particular vector of length n into z, candidate code word I should say here, Okay, so number of columns of B times Z, that is the length. B is a vector. Okay, that is it. So that's nice enough. So we had a B here. Size of B was 46 by 68 and Z was 20, if you remember. That was the expansion factor. So let me generate a random code word, or first thing is so let's generate a code word and then see if this works out. So C is so my code word needs to be 68 into 20, right? So I'll do rand I think. Let's do a help rand I think I know the command, just being very sure. Yeah, sure. So you can do this rand I, if you remember 0, 1, 1, 10, this should give you random bits. Okay, so let's take a random vector. One comma 68 into Z. Okay, and then we can do check code word B comma Z comma C. Okay, so it is complaining about matrix dimensions not agreeing. So one needs to go there and then change what you get at the output here. So I think maybe I made another mistake here. So this one we can conjugate. So this, if we do, I think it should work. Save this. There you go. So it's 0. It's not a valid code word. It's very unlikely that we will find a valid code word. Okay. So one way to definitely find a valid code word is to set this as zeros of 1 comma 68 into Z. Now in this case we should get 1. We do get 1. So it seems like we can't find a code word randomly. That's obvious. You won't be very easily to find a code word. You can't very easily find a code word at random. But at least this is working. It seems to be working. We'll actually generate a valid code word and see if it works out or not. Okay. So this is just a check. One can of course make this all sorts of efficiencies improvements possible here. If you're interested, you can take it up. Okay. So it had two ingredients, multiplying shift and this. Okay. So now we are ready to write the actual encoder. Okay. So let's write that. So 5G NR LDPC encode. Okay. So it's okay. Nice enough command. The base matrix needs to be given, the expansion factor needs to be given, and the message needs to be given. Okay. So for now, I'll take my B and Z as the same as here. Being a little lazy, just copying from there. B is the base matrix, Z is the expansion factor. The message will be the message vector length equals number of columns of B minus number of rows of B multiplied by Z. Okay, so that's got to be the message, and the code word. So what I'm going to actually put out will be code word vector, the entire code word vector. Okay, so length is going to be number of columns of B multiplied by Z. Okay, so you can go ahead and later on, if you don't like it, you can. Did I make a mistake here? Oh, it can't start with a 5. Okay, so I'll just leave it as NR LDPC. Okay. So there you go. So all that's done. So from now on, it's sort of the generation of the code word and the checking are sort of similar. So you'll see we'll start in the same way. Mn is size of B. Okay. And you know, the first 4 rows alone are a little bit special, as in I have to do them slightly carefully and then compute the first parity. Once I compute the first parity and the second parity, third parity, and so on, go on in sort of a very sequential fashion. Okay, so the first 4 bits we'll do that separately. So this is the double diagonal encoding. Okay, so the message is given to me MSG. So I need the code word. So code word, we'll assume C word equals zeros of 1 comma n times z, right. So that's my code word. So I can actually assign the first, so 1 colon m n minus m times z as equal to the message. This is a useful way of checking in case your message is not of the correct length. This will complain. So this is good to have right there. Okay, so then we start with the double diagonal encoding. So the double diagonal encoding is going to give you the first 4 parity blocks. Okay, and how do I do this? This is not very difficult. So for I equals 1 colon, if you remember, I need to do n minus m. Okay, so I have to do the overall parity. So it's good to keep like a temp here. Temp is zeros of 1 comma z. Okay, so this is going to be my temporary thing that I keep adding for j. So I equals 1 to, I'm sorry, here 4. Okay, so I make this mistake. This is the rows. Okay, so these are the rows. Row 1 to 4, and j is 1 colon n minus m. Okay, so this is message columns, right? So what do I do for each I and j? I'm going to say temp equals mod of temp plus mul shift. Okay, so some spaces here for making it more readable. Mul shift of the corresponding message part, right? So that's going to be, you can either use the message or the code word part. I'll use the message. Message of you need j minus 1 times z plus 1 colon j into z. Okay, comma b of I comma j comma 2. Okay, so this is going to compute at the end of this loop. Temp will be all of the message in the first row, second row, third row, fourth row, all of them added together. So when this happens, if you remember the double diagonal structure, the P1, P2, P3, P4, P2 and P3 and P4 will get cancelled. P1 alone will remain. The first and the fourth row of P1 components will again cancel, they will be equal. Only the second or third, whatever it is, will remain. Is that right? So I have to now look for what is in the second and third row in the parity part and then do a shift accordingly. Okay, so I'll do that little bit of calculation here. So once again, what is so I try to find the double diagonal for the parity, what multiplies the parity. Okay, so that I need to find. So that's either there are 2 possible values here. It's either b of 2 comma n minus m plus 1 or b of 3 comma n minus m plus 1. So what I'll do is I'll take p1 shift to be equal to this. Okay, so or maybe I'll do it slightly differently. If this is equal to minus 1, p1 shift is equal to b of 3 comma n minus m plus 1, else p1 shift equals b of 2 comma n minus m plus 1. So let me show you where this is coming from. So you can go and look at the 220, for instance. If you look at the parity part, okay, so you see this is the first row, this is the double diagonal part, the first row of the double diagonal. you see there is 1 0 0 0. So, this is the second row of the double diagonal, third row of the double diagonal, and fourth row of the double diagonal. So, you see these two are the same and this will cancel. So, P1 will just be multiplied by this guy. Okay. So, this happens in the 1 2 20. If you go to 2 1, notice what happens here. So, this is the double diagonal part, right. So, first row of the double diagonal part, you have 0 here, and this is actually minus 1, and this is 1, and this is 0. Okay. So, these two are going to be equal. So, the first and the fourth will always be equal, they will get cancelled, but there will be a remaining shift which is either the second one or the third one. Okay. So, you have to just sort of keep track of that. So, that remaining shift, whether it is the second or the third, I am taking care here. So, this P1 shift will either be the second value or the third value depending on which is not minus 1. Okay. Maybe there is a better way to write it, but that is what I am writing. Okay. So, this is the P1 shift. So, this P1 shift is what multiplies the P1. Okay. So, I have to undo this from temp to get P1. Okay. So, P1, okay, which is actually C word of so, this is the n minus m plus 1 component. So, it is n minus m times z plus 1 colon n minus m plus 1 times z. This is the P1, the first parity. This is null shift of temp, comma, it is not P1 shift, P1 shift got multiplied by this, I have to undo this. So, that would be z minus P1 shift. Okay. So, one needs to be slightly careful here. So, the only confusion is what if P1 shift is 0? Okay. If P1 shift is 0, I am putting in z into the null shift. If I put z into the null shift, what will happen? It will go z plus 1 to end and then 1 to z. Okay. So, it is consistent, putting z into the null shift is kind of reasonable. So, I do not have to do any more adjustments here, everything else will give me the correct value. Okay. So, this gives me P1. Is that okay? So, think about what I did here. I did quite a few things. I went through the first 4 rows, I XORed all of the first 4 rows and then looked at what was remaining. It was just P1, and then found the multiplying factor matrix for P1, and then I did the inverse of that to get P1 itself. Okay. So, that is what happened. Okay. So, think about this and then convince yourself that I have not made too many mistakes. I think it is okay. Finally, we will see if the code word is valid or not, right. So, that will tell us whether we are on the right track or not. Okay. So, now from P2 onwards, okay. So, to find P2 we use the first row. So, if you remember, you can go back and look at it. To find P2, now once the P1 is known, we find P2 using the first row, P3 using the second row, P4 using the third row. Then after that, this will this is sort of redundant, and then we will make a jump. Okay. So, that is the idea here. We make this little jump and then we go through. Okay. So, there are various ways to write this. So, let me do that right away. Okay. So, we will do it in 2 steps. For I will do it once again for I equals 1 to 3. This is the first 3 rows for computing P2 to P3. Okay, it's becoming a little bit long, but that's okay. Let me put some space here so that it comes out okay. So, first row, and then once again I need to just do for j equals 1 colon. I mean, a lot of people who watch this very closely will tell that I am doing a lot of computation repeatedly. I think it is correct, I agree with you, but just like I said, we are not trying to be very efficient here. You can make the program more efficient if you believe you want to do it, but this is just to get one encoder out. Okay. So, notice what I have done here. I went from I equals 1 to 3, and then j equals 1 to n minus m plus I. So, I need to look at n minus m plus I columns. So, if you look at the first row here, I go up to n minus 1, and then I need to look at this also, right. So, this one also plays a role, that is important to know. Okay. And what do I do here? You can have directly, you can have something like this C word. So, maybe we will make it a little bit more efficient, right. So, we will keep temp as just to make it look a little better, 1 comma z, and then I will do temp equals mod of temp plus mul shift of C word of this is just the same as before, z plus 1 colon j times c comma b of I comma j comma 2. Okay, and then once this computation is done, you can assign C word of n minus m plus I times z plus 1 colon n minus m plus I plus 1 times z to be equal to temp. Okay. So, this takes care of P2 to P4, I am sorry, find P2, P3, P4. Okay. So, this takes care of that, and then for the remaining part I have to go from 4 to the end for I equals 4, no, not 4, 5 colon m, okay, remaining parities. So, notice there is no need to do any shifting here. The shift gets so it is all identity, right. So I am sorry. So, if you notice, it is all identity after this, right. So, it is all identity 0 0, even here it is all 0 0 0 0 0 0 only. Okay. So, and it is also, if you see, this whole part is minus 1. So, it is enough if you stop in the columns up to this point, you do not have to go beyond this. Okay. So, for j, so you can do the temp once again just to be a little bit clear, C, and then you do for, oops, I think something went wrong here, for j equals 1 colon n minus m plus 3 or 4. Okay. You do not need to go beyond that. Okay. Okay. So, once again, notice what I am saying here. So, you have n minus m plus 1 here, n minus m plus 2 here, n minus m plus 3 here, n minus m plus 4 here. Okay. So, after that there is always 0. So, no need to worry about all the other things. So, from P5 onwards you just have to stop, you can stop here. There is some 11 etc. here. So, most of it is 0, but nevertheless one can take care of this. Okay. So, I am going to go through the whole thing and then write the same sort of command. So, maybe I should just copy paste here. Oops, sorry. Can copy paste here, mod of temp multiply. I think I do not have to change anything here, it is exact same thing exactly. So, and then C word. So, even this I think is exactly the same. Okay, so I think that sort of ends the whole thing. It's good to check the last value. So, supposing I is m, you have okay. So, I think there is something that's slightly wrong here. Let me just check this out. Here you need a change. I think this j I think is okay. The I here, the fifth is okay, but the first I needs to do I think you need a minus 1 here. Okay. So, this is correct. Okay. So, this is because I shifted down by 1. So, you need this little bit of adjustment to make this work. Okay. All right. So, I think that should take care of most of the things. I think I have not made any mistake here. So, except for maybe should I worry about the column or row problem? I think it's okay. Everything looks fine here as far as I can see. Well, the proof of the pudding is in the eating. So, let's try and run this and see what happens. Okay. So, if you run it, hopefully it should work. I think I have not made anything significantly wrong here. Nothing has gone wrong here. Okay. So, let's try to run this. If there is a problem, we'll deal with this. Okay. So, my C is going to be so I need to generate a message now. Okay. So, my size of B is what? 46 by 68. My message, my expansion factor is I think 20. Okay, so my message is going to be randi 0 1 comma 1 comma 22 times, right, n minus m 22 times z. Okay, so this is my message, and I'm going to let my c be nr LDPC encode b comma z comma msg. Wow, there's no error. Okay, at least no runtime error. So let's just check whether it's a code word or not. Right, so this is, it's 1. Okay, it says it's a valid code word. So the message was random. So if you look at the message, it had a lot of zeros and ones, and c word, it has a lot of, sorry, did I put c word here? C, I'm sorry, the code word became a lot of zeros and ones, and then when I did check code word, I got 1. Okay, which means the encoding happened and you got the correct code word, right? So remember once again, what does check code word tell you? Out equals 1, code word is valid. Okay, so you can try various other. So the encoder is basically working. So let's try one more. We'll try loading the other one. So the other example I gave you was what was the other one I pulled out? 1 2 20, right? 2 1 48. So let's try 2 1 48. Okay, so b equals 2 1 48. Okay, the size of b now, it should be 42 by 52. Yes, it's 42 by 52. And let the message be 10 times z. Okay, so z also I should have made, I'm sorry. Z is 48. Okay, and message is 10 times. Okay, so this is a random message generated 10 times c. And let's see, we can encode this and check. So 1. Okay, so this also works. This piece of code, I will make it available to you. This encoder for the LDPC code in the 5G standard, and this check code word and the null shift, and then you can run it yourself and you will have the encode. So you see how this worked in MATLAB. It's quite easy to write. It's just a few lines of code. You just need the base matrices and then go through them and write it off. Okay, so an implementation of this is quite easy to do. Hopefully this was clear to you. And there you go. You have an encoder for the LDPC codes in the 5G standard. Okay, any LDPC code you pick, you should be able to encode now. Okay, so now the next step is the decoder, which you might imagine is significantly more complex, but actually it's not. See, the decoder itself is also very easy to write down. We'll write a similar program involving the base matrix, and you will have the decoder as well. Okay, so that will be the next stage. Okay, thank you very much.